Hey, welcome back to Fan Mama Physics. You can tell from all these questions how exhausting it is for you as well as for me, but you know, it's just we just gotta get through this. But hey, guess what? There's some good news. Hopefully, I'm gonna add in another page here, so we're not so crammed. I can actually have space to write, so I'm not stressed out about space. Okay, here we go. A proton was shot directly at another proton at 0.1% of the speed of light at a faraway distance. How close does this proton get before it comes to a stop? Okay. Well then, I'm going to use this top page for the diagram and the bottom page for the actual calculations. So, okay, so it's a proton towards a proton. So here's a proton here. This proton is very far away. We can assume it's a distance of infinity, and we're going to shoot this guy directly at the proton. So assuming it's in a direct straight line. If it's not in a direct straight line, this proton's probably going to veer right or left, or what, of course, in a 3D space will be in multi-directions. But assuming it's shot at a very straight line, and it's like the only thing in the universe, so nothing's going to change its direction or anything. Very hypothetical. We start off with a speed of 0.1 at the speed of light. So that's 0.001 times 3 times 10 to the power of 8 meters per second. Effectively, that's just 3 times 10 to the power of 5 meters per second. Okay? How close does a proton get before it comes to a stop? Again, this has to do with the change in potential energy, or actually, this would be the change in kinetic energy to the change in potential energy, meaning that this kinetic energy, these protons are very far away. As this proton's getting shot towards this proton, imagine if it's going to get very close to the other positive charge, it's going to slow down. That kinetic energy will get converted into potential energy as it gets closer and closer to this other proton. And it's going to get to a certain point somewhere over here until its speed reaches 0. So that's actually initial speed there. The final speed has to be 0. That's the closest it can get based off of how much kinetic energy it had to start off with. And this is what we want to find out. We want to find out how close does it get. So I'll label as R final. And don't forget, the potential energy of two charges at a faraway distance, we assume to be infinity, is about 0 joules. So essentially, how much kinetic energy it has in the beginning is going to be equal to the potential energy that we will get over here when it comes to a stop. So the kinetic energy initial is just going to be equal to the potential energy final. Very nice and clean, okay? So this is 1/2 mv, actually mu squared is equal to k, and this is what, 2 protons? So that's just 2 elementary charges. Actually, I'll put protons so it doesn't confuse you. That's just p times p, the charge of a proton times charge of a proton, divided by this distance that we don't know what it is. So let's solve this one. And so much space. It feels so much better. Okay, so solving for r, gonna move r to the top just so it doesn't clutter the bottom. We need the bottom. Actually, no, we need r on top just because otherwise there's no way for us to solve for r. Okay, and then next up we're gonna move everything over here on the other side. I'm gonna first multiply both sides by 2 just to get rid of that one. I get and also I'm going to need to divide m and u squared. Okay, so if I do all that, this is going to give me r is equal to 2 times k, charge of proton times charge of proton, divided by mass of proton that was moving, and its speed squared. Okay, so if I do everything, this is 8.99 times 10 to the power of 9. The charge of a proton is 1.6 times 10 to the power of negative 19. And since I multiply another proton, so I'm just going to square that one. And again, these are 2 positive charges. I don't need to worry about putting in that negative sign. The mass of a proton, as we talked about earlier, you can find your data booklet, 1.673 times 10 to the power of negative 27 times its speed, which is 1.1% of the speed of light, 3 times 10 to the power of 5 meters per second, all of that squared. So let's put all this in the calculator. I get 3.056, which I'm going to round to 3.1, I think it's 2 sig figs, times 10 to the power of negative 12 meters away. And I think that's a little different from the key. So after double checking, this is the correct answer. So probably what happened above, this is by order of 4. So probably in the above, there might have been a typing mistake or something. But if you double check this one, this should be the correct calculations. Okay? So this is the final answer. This far away. Okay? The key is wrong. Great! Alrighty! So, thank you for watching and getting through all of these examples. I wish you best of luck with your practices. Fan Mama Physics, signing out!